Yes, I suggest that we start with the announcement. So, good day, everyone. I hope you're doing fine. Welcome. So, I'm very happy to kick off the second year of the seminar series with an excellent speaker, Professor Henk Nijmeijer. So, I think that Henk doesn't need much introduction. So, Henk is full professor at the Eindhoven University of Technology at the Department of Mechanical Engineering, very well known for his pioneering contributions on nonlinear dynamical systems and control, with research which is at the same time very deep, but also very broad, spanning a whole range from fundamental theoretical contributions to a variety of real-life applications. Among different honors, Henk has been IEEE Life Fellow and IFAC Fellow. So personally, I know Henk also very well. So 15 years ago, in 2007, I've been postdoc in his group, where I had a very nice time. And since then, in fact, we've always been in contact and collaborated beyond the scientific aspects. So I'm very happy, Henk, that you accepted to give the opening talk of this year of hopefully successful TDS seminars with an overview of your work on synchronization in networks. So I give you the floor in a moment. After the talk, there will be the opportunity to ask questions. And you can also, if you prefer, already indicate questions or comments in the chat, which I will monitor meanwhile. So Henk, thank you again. And if you're ready, I give the floor to you.
Okay, Wim, thank you very much. Thank you for giving me the opportunity to give this talk. I'm going to talk about work that I've been doing for more than 2 decades. I mean, it's really a tribute to my grandfather, Christian Huygens, synchronization. It's really some field I love, I very much love. I decided to add also networks, because if you work longer on the subject, you have to broaden it a bit, and so it's synchronization and network. And because of the technology on time delays, I decided also to add today time delays. And perhaps there's a bit more. It's at the moment in the Netherlands almost freezing. There is still snow visible, which is quite surprising at the day beginning April. So I think there's nothing better to do than sit indoors and spend my time in giving this presentation. Actually, you see already on the slide 2 illustrations of what synchronization is about, and I hope to explain that further in what follows. And my talk will be a very superficial talk in a sense. There will be very little technical detail. Actually, I try to avoid almost all, but I want to give you a flavor where the interesting aspects appear and how potentially one may approach questions on synchronization. And here and there, perhaps even more than desired, I will also open up the floor and make suggestions for what is still open there. I think I end up with more open questions than solved ones. But synchronization is sort of what you see here pictured in the 2 photos. You see a kangaroo hopping with the 2 legs next to each other. It's really a periodic synchronized motion of the kangaroo. So synchronization is it's about dynamics, it's about simultaneous motion of at least 2 systems. And you see also the walker beneath. You see here, if you look at the legs, and if you wish, you may also look at the arms of the person, you see again, there is a sort of evolution, but in this case, instead of what we see with a kangaroo, we see a sort of anti-phase synchronization of the limbs of the person. And this is sort of what we see all around us. And if you get intrigued by it, you will discover more and more examples by yourself. And this is what I like to stress, this you can have this not only with two systems, separate systems, but even many, many more. And I'll come back to that for sure in a minute. This is these are sound bites I borrowed from Ikio Aihara. Before letting the sound bites go, I first want to say a few words on this. This is about Japanese tree frogs, and what you will hear is these tree frogs exhibit synchronized calling, and I want to really let you hear this, so I won't interrupt on that. You hear first the one. Sorry. And now I go to the other one. Gee. So you must imagine, this is really research work done by Ikio Aihara. He was bringing two of these tree frogs sitting in boxes and brought them, say, in his lab environment. And the two tree frogs, you could hear they were sort of calling in an anti-phase manner. Quite interesting. And already to understand how that works is a question, but the other question he started to work on was, what happens if I take a third tree frog, also in a box, put it in the same lab environment, and what will happen? Well, I'll pass this question over to you as an open question, because this is very, very hard to answer. Actually, you will see at the very end something very reminiscent to what I'm trying to say here, but in general, it's very difficult to find a fixed pattern. I also want to show you the next one. These are two movies from Kitahata from Japan and his co-workers, where you see a combustion deck, and where on the left you see with candles closer, the lights, the fire is close to each other. You see at the 20 millimeter distance, you see in phase synchrony of the flames, and on the right side, you saw the anti-phase synchrony. Very curious, very interesting. This is what you really can see. And again, I try to heat up you a bit. Ask yourself the question, how is this coming? Why in one case you have in-phase synchrony, and why in other case anti-phase synchrony? And in many cases we don't know the answer, and that's the reason I'm so much intrigued by problems of synchronized system. And this is not biology, and these are inert systems, so that's really an interesting issue. If we go back to, say, Christian Huygens is 17th century work, and he was a Dutch scientist and really one of the giants from his age, from his century. He was close to a bit earlier actually than Newton, and he described actually the first real experiments. You will see in a minute a drawing from him on synchronization. But the main observation he argued is you need a medium. This is the word he used, and what we nowadays are completely standardly call coupling between the systems. The systems, the legs, the frogs, the flames, there must be a medium, a coupling between the systems. That's something you have to think about. It can be mechanical, can be electrical, can be whatever, but there must be a medium. And also to stress that, also the media, the coupling can be, and in many cases will be, static, sort of an output coupling, but it can also be a dynamic. And for today, I'll try to focus a bit more on the situation where there is in the coupling is time delay, which is sort of unavoidable in many cases. And if you think about, if you're very much a car driver, if you think about adaptive cruise control or cooperative adaptive cruise control, you immediately encounter also time delays because simply the communication needed, either using the radar or the Wi-Fi type communication, you will have time delay. Here is my grandfather, as I mentioned, living 17th century, and among others, he wrote this book. You see a drawing on the right-hand side. This is a drawing, and this is what I wanted to show. This is a drawing from one of his notebooks, and coming from a letter he wrote to his father, Constantine Huygens, and he wrote there this setup. It's a weird setup, I must say. You see two chairs and then two pendulum clocks attached to a bar between the two pendulum clocks. And what he describes there, hence, when the clockworks are at a small distance separation, I began to suspect a certain sympathy, as if one were affected by the other. The sympathy is actually sort of the mimicking word for synchronization. Quite interesting. You may ask yourself, why would you ever sort of make a construction as you see here? And there's a beautiful story about that. And I could give a 1 hour lecture, and I do sometimes give a 1 hour lecture simply about why Huygens was doing this sort of work, but I don't have time and I don't want to go into the details of that. What he described actually is in his experiment. He was actually ill when he did this experiment. He saw, in loose terms, what you see here, anti-phase synchrony of the two pendulum clocks. There is also, and there is some evidence from the notebook, but it's not completely sure, that he was aware that you could also have the in-phase synchrony of the pendulum clocks. And if you do the experiment now, and we have done this in many ways, and others also have been working on that, you will see that you can realize also the in-phase synchrony, perhaps playing a bit more with the mass and the pendulum frequency. But what you also will observe, and that's so key here, I asked you earlier, what is the medium? What is the medium between the clocks? What is the coupling mechanism? And it becomes completely apparent here. The medium is, of course, the bar to which the clocks are attached. And realize this, the bar, it must be a bar, and you can't take a stone wall and attach the clocks to that. You won't get this synchrony. After this observation of Huygens, it's quite interesting. There were at least two British contributors. John Ellicott, he reported in the 18th century an odd phenomenon, as he called it, when two pendulums were placed sideways, watch out, sideways to one another, and one of them was always found to stop working after 2 hours. So it's a different outcome than Huygens described, but also realized that here the two pendula are placed sideways. So that's not completely the same thing, likely. And then William Ellis, another one, in actually already beginning 19th century, or second half of 19th century, you see he did the same experiment, and he wrote the pendulum of one clock swing to the left, whereas the other one to the right. And he noticed in his writing on this experiment, he noticed the sympathetic behavior in the two pendulum clocks. By the way, the word sympathetic he uses even in the title of the paper, but there's no reference to my grandfather, Christian Huygens. The diagram you see here clearly shows the anti-phase synchrony, by the way. So this is sort of a description of exactly what Huygens observed 2 centuries earlier already. Now, as I mentioned, I'm not going in much of detail, and I'm not going to show many equations, but there is one thing I want to show here at this point, because it's so basic that everyone would think about it, that I think it's worth mentioning. Of course, if you want to do an analysis on this type of work, you need models, you need the framework, so to say, and ultimately you also want to do the testing. And here I just described the most basic description of what you could say. This is a simplified version of what Huygens was doing. What you see here, a rigid beam connected to the fixed world by a spring and damper. And the two pendula you see here, they are equal. They have the angle with respect to the vertical is phi1, and for the other one phi2. And if you then write down the equations of motion, you get the equations really as I describe here. This is just Euler-Lagrange straight ahead. The U1 and U2 here are basically potential external forces, but if we disregard anything as friction or so, we won't have any need for U1 and U2 different from 0. So I'll take for the time being just to shape the experiment or the model. I take U1 and U2 equal to 0. So ideal world, no friction, no damping whatsoever. My clocks will run, and then you have here the model again. Energy, you can write down the energy straight ahead. You see the sum of potential and kinetic energy, and take the time derivative of the energy, and you get dissipation. The time derivative of the energy function is minus dx dot square, which is always semi-negative, negative definite. X was here the displacement in horizontal direction, and you may remind what I showed you in this animation. Earlier you saw the platform or the beam making small motion in horizontal direction. This sort of what you see right away from this stability is a direct consequence. If you apply LaSalle, you also find all solutions will tend towards the anti-phase situation where phi1 is minus phi2, phi1 dot is minus phi2 dot, and x is 0, x dot is 0. This is the most advanced maths I want to show today as in terms of equations. But this is something to keep in mind. Now I'm moving forward, and I leave the arena of the two clocks for a while, and I move forward to a network. Networks are everywhere, and traffic, internet, biology, but brains are the entity I'm thinking about. And you will see later on, my experiments are really done with an electric brain. Now, what is just to shape the thought, going from the two oscillators that we considered so far in the Huygens experiment, a brain is something totally different. The order is 10 to the power 11 neurons, and you have between neurons couplings of order 10 to the power 3. So it's a drama if you want to do here a full math equations. This is dramatically big. But there are some interesting aspects, and there is some interesting here also for control people. Each neuron is an input-output system. The input is the synaptic current, and the output is the membrane potential. So here it helps actually to have a sort of control mind and thinking about that. And how this behaves, the input-output behaves, that's something different, or what is the kind of input that does, for me, is at the moment not so relevant, but it is something to keep in mind. These are input-output systems. So if I start to couple them, even with only few couplings, then you have a sort of nice network for them. So in order to get there, I need a few, so here is some math, but I need a few basic equations. If I have a dynamic, say with M inputs, M outputs, so a square system, I call this system semi-passive. If sort of the system is passive outside some ball. I guess most of you are familiar with the notion of passivity. Passivity, typically you say there must be a function phi that is, or the function phi, there must be a function phi such as phi dot is smaller than the product of and the power that delivered y transpose times u. But here I add is minus hx, where hx is non-negative, positive outside some ball. So the passivity is outside the green ball. And what does this say? It says, okay, similar to strictly a semi-passive system behaves like a passive system as long as the internal state X is large. What happens inside can be chaotic, can be oscillatory, I don't mind. So don't get confused. It's very realistic to think about this sort of semi-passive systems also in biology, because there's no free or unbounded energy generation, but perhaps there can be energy generated, say, through food or in other means. So that's the background here. And of course, what is nice, and that's the reason I specifically focus on semi-passivity here, is if I take an output coupling of the form, say, U is phi of y, then, and satisfying a sector condition, like I wrote here, y transpose phi y is smaller than or equal to 0, then I always have ultimately bounded solutions. So if I couple many of these systems, infinitely many if I wish, like in a brain, and coupling with such type of feedback interconnection, then I have bounded solution. That's of course a key thing. If you look and if you're interested in synchronization studies, the first thing that is often forgotten is sort of a check. Are the closed loop system and the closed loop trajectories, are they bounded? Now, the next notion I play with is, say, if I have a system like written here, C dot is G of C W, W as sort of an input. The system is called the convergent if all solutions are well defined for a certain set of input functions, and in addition there is a unique solution set bar depending on this input function towards all solutions converge. So the idea here is if you apply a specific input W from a bounded set capital W, then any solution of the differential equation will ultimately converge to that specific solution set bar of W. The typical thing of this is a convergent system has the property that it forgets its initial condition. So whatever input if you take any input and you take arbitrary initial conditions, ultimately the two solutions will converge and follow the same trajectory. This idea of convergent systems has a big history, not only in Russia. Demidovich from St. Petersburg in the 50s, 60s was really one of the fathers of this work. But you also find work in the US and in Japan, all around with slight different terminology, but all about the same thing. A sufficient condition for convergency is, say, if you take the symmetrized Jacobian of G, so G of the Jacobian of G with respect to C times P plus P times the Jacobian of G times C must be semi-negative, must be negative definite. So there must be, and this matrix P is supposed to be positive definite, so symmetric positive definite, and this symmetrized Jacobian with respect to the matrix P must be negative definite for all C and all W. Quite interesting result. And if you start to think about it, you will immediately recognize you can prove this straightforwardly by applying standard Lyapunov theory. But this gives you an idea of how convergent systems are defined and what conditions for them are necessary. Now, if I go back, I was thinking, referring to a network, I need one more notion. I'm going to couple the network. So think about my large brain or a system consisting of many identical systems. I call it diffusive coupling. If I take as input to system I a sort of weighted difference of output of that system I with respect to all connected systems to it. So typically UI is minus gamma I1, Y1 minus YI, etc., where these gammas are sort of the weight of the relative mismatch of output with the ith cell between the first output and so on. So typically, this diffusive coupling defines a matrix gamma as you see at the bottom of this slide. And the diagonal is typically the sum, or the diagonals is typically the sum of the corresponding gammas. You also see there is always an eigenvalue, a left eigenvalue consisting of all ones, an eigenvalue 0. Now, so it's singular, has rank n-1, it's symmetric, it's positive semi-definite, and the eigenvalues are just lambda 1 is 0, and then the next one is lambda 2 is, and that is a serious restriction or assumption I make. The next one is really positive. So it's really, I'm making the assumption that gamma is singular of rank n-1. So then the second eigenvalue is indeed that lambda 2 is positive. Now, why did I do all this? If I couple now k identical systems, each of the system is these systems are diffusively coupled, and each system is strictly semi-passive, then I have for this type of network automatically ultimate bounded solutions. There you see again that claim of semi-passivity coming back. And our first result I want to show here is for these identical systems in this specific structure, I can ensure that if this eigenvalue lambda 2 of the coupling matrix gamma is sufficiently large, is larger than a certain threshold, then I will have asymptotic stability of, say, part of the diagonal. So I will have the systems will synchronize with each other, be it in chaotic motion, oscillatory motion, whatsoever, they will synchronize. So that's the good thing. And the good thing here also is it says, okay, I have the synchrony provided lambda 2 is sufficiently large. I see there's a bar missing on lambda, but okay, lambda 2 should be sufficiently large. And if in terms of the coupling, let me go back, here is the coupling. So basically, of course, I'm saying the first non-zero eigenvalue of my matrix gamma must be sufficiently large. So if I can manipulate the weights in the coupling, in the diffusive coupling, I can certainly ensure the synchrony. That depends, of course. That may not be the case in a brain, but this is sort of very interesting to see. Now, why did I push this? I want to push this one step further. I want to include also time delay. So I take here, I also allow now, instead of the coupling that was previously without time delay, so the tau was 0, I'm now allowing time delay really of this type. These are also called non-invasive coupling, but if you wish, you could also consider invasive coupling. So there, all the neighboring outputs are sort of measured with a time delay tau, but the output itself from the side cell is not time delayed. I'm not going further into the non-invasive case, but actually everything I'm going to say will hold true also in that case. So I have now two parameters to play with. That is the coupling strength, basically here, and this is the time delay. And of course, I still have this interconnection matrix, gamma, or structure matrix like gamma. Now, the interesting thing is this. Here you see the same setting, same sort of decomposition. I assume each system to be strictly semi-passive. I do have, again, the semi-passivity with respect to a function capital H in this format. So here there's nothing different from what I showed before. And I also require each subsystem and a non-input equation, so to say, to be a convergent system. If that is the case, then there exist positive constants, sigma star and gamma star, such that if your coupling strength is sufficiently large, so exceeding the sigma star, and the product of sigma and tau, the time delay, is sufficiently small, smaller than this gamma star, then I have asymptotic stability of the subset of the diagonal element. So basically I have the systems will synchronize in that specific regime. So what you get is a regime like this, drawing in sigma tau space. You see the gray area in that region. I will have synchrony of the systems with the diffusive coupled system with time delay. And the interesting thing is sort of you can again recognize, okay, I need the coupling to be sufficiently large and the time delay should be sufficiently small. I mean, I think all of you are familiar with if the time delay becomes too large, then for sure any stability result becomes problematic. And that's exactly why you get a picture like this. So far, so good. How can we work this out? Because, and I already mentioned, these larger networks become extremely complicated. But there's one result, and this is, I purposely wanted to show it today. It's work that I did partly with Wim Michiels and a couple of other people, scaling. And why is scaling interesting? Scaling allows to make a step to go from a network of two cells towards an arbitrary large network, or at least a larger network. So, and how does it go? The result is by itself pretty simple to formulate, but the proof is much less straightforward. Of course, it brings all ingredients of time delay, but also of standard type of Lyapunov analysis, kind of Lyapunov analysis. I should be a bit careful there. Suppose I have, because here I'm sort of trying to formulate it. Suppose you have, as a start, two systems that are coupled, identical systems, semi-passive, identical systems. They are coupled by a non-invasive U1, U2, so it's really a symmetric coupling. And the input received at system 1 is minus the input received at system 2. And suppose, according to my theory, the system synchronize, say, for sigma and tau in a region S star. So in the region in sigma tau space. Now define the Laplacian as the diagonal matrix minus the matrix A, and let the eigenvalues of the Laplacian be lambda 1, lambda 2, etc. So lambda 2 is the first non-zero eigenvalue, and so forth. Now, then K systems will locally synchronize. So if I couple K systems with the coupling matrix or the Laplacian L, they will synchronize if the pair sigma tau is in the set S, which is in the intersection of the set Sj and the Sj set. That's a very interesting set. It is formed as the pairs of 2 sigma divided by lambda j, comma tau, where sigma tau should be from S star. So you start with this S star, and then you can make S1, S2, S3, S4. You can make that in this manner up till the set Sk. And if you have that, your sigma tau in this set S as the intersection, defined as the intersection of all S, J's, then you have synchrony again. So it's a very powerful result, as it allows you to go from of 2 systems coupled, bidirectionally coupled, towards a much more general structure. Say you think about your brain structure. Now here is an example. This is the Nagoya, what was his name? System. And we used, this is a 2-dimensional simplified model for a brain, the dynamics of a brain cell. And with certain setting, if you do simply a simple simulation exercise, you find this is the region where the 2 cells synchronize. Actually, precisely of a form that I announced earlier. Now, if I take in the next case, the network as described here, every cell is coupled to its near neighbors and a few other extra links like you see here. I then make the intersection as I announced. I make that intersection, and you really find ultimately this is the region where you have the synchrony of all cells in this network. So it's a quite interesting sort of observation. Of course, you need to compute the Laplace and the eigenvalues, but once you have done so, you compute right away the region where you have full synchrony in the network. So in that sense, it's a very powerful result. Actually, as an open problem, the other way around is at the moment a no-go. If you have a very large network where all cells, or where given the topology, the network structure where you have synchrony, and if I would reduce it to a smaller network, there's no way, at least known to me at the moment, that tells you, okay, also to conclude I have synchrony in the smaller network. So that's a very interesting open problem there. Now, we played with that, and I mentioned already before, and we built in my lab years ago an experimental setup, an electronic brain. And we took for that a single cell, an electronic version of a Nijmeijer neuron. It's a slightly different model than I just used in the simulation example in the previous slides. But this is one of the other neuronal models that is fairly well adopted in the neuronal world. And I'm considering for the time being invasive coupling. And the setup allows, I think we started with about 20 cells. The setup was quite old, 20 cells, but what we particularly insisted on was to be able to create arbitrary couplings and arbitrary time delays, so that you really can have a brain environment where you are free to design the coupling and time delays. And here we took invasive coupling as in the experiment. And now, if you start to do this, something interesting comes up, and I really like this part extremely well, because you must realize if you try to build an electronic cell mimicking the dynamics of a Nijmeijer neuron, the components from which you build the cell are, of course, coming from Fabric, are sort of equal to a certain level, but they are, of course, not perfectly equal. So if I want to talk about synchrony of 2 cells, or maybe later on more cells, we have to adopt and accept that there is a sort of small mismatch outside. And that's an interesting thing. And I wrote here practical synchronization as lin soup, smaller than equal to epsilon. But of course, in an experiment, this is totally meaningless. I mean, you want in a finite time horizon, you want to have this small, sufficiently small. But what is finite time? What should I take as sufficient time for convergence versus what is the acceptable sort of level of noise, so to say? Now, anyways. Could say much more on that. We have published more work on that. I leave that for a moment. Theoretically, for the two Nijmeijer cells, I would find synchrony for gamma equal to 0.5. In the experiment, it's about 0.6. And typically, you see the synchrony, well, it's pretty close, but you see an epsilon band around the diagonal. So it very well illustrates what I was saying. But it's of course very critical if you have no idea, very critical how to select your epsilon versus coupling strength. How large should your coupling be in order to guarantee your synchrony, or was your epsilon too small, or is your epsilon too big and your gamma is too small? These are really things you have to think about. Now, if you do play with different topologies, you see here in total 6 topologies. We do 1-to-1, the triangular setting, the 4 cell. You find sort of the 4 diagrams like you see here. And I'm showing this in retrospect and by after the work with Wim in particular, we know better how to understand, but this were the first experiments what we were doing. And it's interesting to see. It's interesting sort of these are experimental outcomes and quite nice. But you start also to realize, apart probably for topology D, which is the line topology, maybe you can understand it. You see there is some similarity in these figures, in these triangular shaped areas of synchrony. This is what we observed first experimentally. And later on, we realized really we need to form these sets S and then the intersection of these sets. I just recall the slide, where is it? I just recall this result. So this for me was for a very interesting sort of result. The experiment finally led us to a theory about this scaling. And yeah, for me, I still find it rather unique that experiments really help you and drive you towards a particular theoretical result. I assume, Wim, I can continue maybe for another 5 to 10 minutes. Is that okay?
That's okay, Henk.
Okay. Now I want to go a little bit more beyond what I've shown. Some of the results I've shown are, well, we've worked on this for many years, but this is not so surprising. Actually, this network, I want to show you shortly. This is a network of 10 cells. And actually, it's sort of by coincidence, this network was sort of taken by the student who built my electronic brain. I asked him, okay, what's your favorite network? And for some reason, he cooked up this network. So 10 cells. Again, it's extremely small for a real brain, but at the same time, very interesting what will come out. The cells are sort of connected. The topology is as you see in this diagram, and then what happens? What is very interesting is the following. So I take all the couplings equal, by the way, I should say that. And if you take the coupling sufficiently large of order 1.5, and the cells are really these Nijmeijer neurons, then you have full synchrony. So all the cells will synchronize when you have couplings larger than 1.5. However, if you take coupling strengths of order 0.8, then what will happen? And really, it's very simple illustrated here. The red cells will synchronize, the blue cells will synchronize, the green cells will synchronize, and the yellow ones will synchronize. But they will not synchronize with each other. And regrettably, or maybe not regrettably, the cell 2 and cell 9 will not synchronize at all. This is a very, very interesting result, and I like to draw your attention particularly to the cells 1 and 3 or 8 and 10, because 1 and 3 synchronize, but there is no direct connection between the two cells. And just to, as a small detour, this is very much interesting for people studying brain dynamics, epileptic seizures and the like, where typically it is known that certain regions in the brain start to synchronize as a sort of prelude of an epileptic seizure. And what you see here, it can happen just that there are parts of the brain, here only two single cells sort of start to synchronize without being directly connected. To me, a very amazing result. You can, I think I skipped this a bit. Of course, you can have also partial synchrony, but I think I want to skip that for given time. Actually, it's interesting to see a structure as with 4 cells coupled with say equal coupling between 1 and 2 and 3 and 4, equal coupling between 2 and 3 and 1 and 4, and then of course depending on your coupling strengths K1 respectively K2, you get non-synchrony, full synchrony, or synchrony between 2 of the cells and not between the other ones. It's sort of typically here underneath is a bifurcation diagram. Why I'm going a bit faster here, but what I wanted to raise as a question, this is work done partly with several PhDs from a Marie Curie European Union project. We asked the question to one of the students was, if you have, say, time delay coupling, say, and you have a network as simple as this one, or slightly more, let's say with 4 cells, there is some time delay. What are possible synchronization patterns, and how robust is that? I mean, think about the robustness I mentioned already earlier in terms of an experiment. And so possible synchronization patterns could be, yes, okay, seek for bifurcations as I mentioned here, but of course it can also be say that only 2 of the cells synchronize and the third one not, and then we are more in the context of what I've shown in the SAND class. Now, this was the question, and sort of you see here a definition, say you have the 3 systems. This is sort of an attempt to draw in 3D, in a 3-dimensional graph. You see the x1, x3, x2, x3 axis, and say, suppose x1 and x2 synchronize and x3 does not synchronize. And you have a partial synchronization, and perhaps you want to have some robustness, then every 3x3 ultimately should be bounded between the 2 blue planes where, say, x1 minus x3 is smaller than some threshold value, epsilon or mu is called mu. So that could be a sort of partial synchrony. But when do we have this? It's not so easy. Of course, we derived, the student derived here some interesting results, very much based on LMI type inequalities. And yes, you get some result, but it's extremely conservative, as you may expect. He played with, or in Masrow's network, really in experiment. And what you see here is, and this is the structure, the topology, sort of 4-cell structure. And you see here coupling strength and time delay, because we are back with the time delay. And then you see here a very interesting piece, a larger portion of the what you see here. You have full synchrony, but you have partial synchrony in the region PS2, likewise in PS1, where the partial synchrony in region 1 is cells 1 and 2 synchronized, and 3 and 4, and similarly 1 and 3 synchronized, and 2 and 4 in case of the PS2, so in this area. So that's an interesting aspect to see. What is missing, and I really should do this very quickly, I think also given time, is of course what is sort of missing is what are numerical techniques that can help you to explore potential synchrony. I mean, yes, you can try with some of these LMI type conditions for time delay stability, so to say. Another way is sort of use numerical techniques, and I very quickly want to mention that. It's work with Kirill Rogov, again, one of these PhDs at this European network who finished last year his thesis. So as an example, he took, say, coupled Lurie systems, and what he uses particularly is the multivariable harmonic balancing method. And sort of here are the ingredients you seek for oscillatory behavior. Then you also approximate the nonlinearity. And as I mentioned, I think I'm looking at Lurie type systems, so largely linear with only one output nonlinearity. Approximate the nonlinearity by the describing function, and then you have the ingredients to go for an optimization problem. Already a very serious optimization problem to solve, but once you are able to find a solution, you can at least answer, okay, I have a tool to distinguish or to observe synchrony in such coupled network. But that worked, and you see here the outcome of his simulation. I didn't want to show that at the end, but I want to show at the end really an experiment. I hope this is going to work, because the experiment you see here 3 metronomes on a platform which is connected to the fixed world by wires. And what you particularly see is the parameter R, the metronomes, you see they're sort of placed in a ring-like environment. And by increasing the radius, you will discover that you have a different form of synchrony between the metronomes. Here, if you carefully look at what comes out, the 3 metronomes, you have a sort of phase-shifted synchrony of one. Phase shift is 120 degrees between each of the 3 metronomes, whereas here you have really full synchrony of the metronome. So, but the parameter to play with here is the radius, so the ring on which the metronomes are placed is sort of key for what do I have, full synchrony, or do I have the phase shifted synchrony? And the interesting thing is, so this is what we were able to arrive at in our experiment. But if you apply this multivariate harmonic balancing method, you exactly arrive at this conclusion also, which I found a very interesting illustration how powerful this tool could be. I think with that, I leave the presentation, and I'm open for further questions. Thank you.
Yeah, Henk, thank you very much for this very nice and also very pedagogical presentation.